In today's video, let's learn about a linear algebra primer on covariance matrices in modern portfolio theory. At the heart of quantitative finance lies a single powerful mathematical object, the covariance matrix. In the context of modern portfolio theory, pioneered by Harry Markowitz, the covariance matrix is the cornerstone of risk measurement, diversification, and portfolio optimization. It provides a comprehensive framework for moving beyond the analysis of individual assets in isolation and instead focusing on the intricate web of relations that defines the risk of a collective portfolio. The matrix is denoted by the symbol sigma and is a square matrix that contains the covariance between each pair of asset returns with a given universe. It is a natural generalization of one-dimensional concept of variance to multiple dimensions, offering a complete characterization of both the individual volatility of the asset, more importantly, the tendency to move together. To understand the geometry of portfolio risk, one must first understand the algebraic components of the covariance matrix. For a set of n assets with returns represented by a random vector r is equals to t, the covariance matrix is an n into n matrix where each element sigma of ij is the covariance between the return of asset I and the return of asset j. So this n into n covariance matrix looks something like this. The term cov Ri, Rj is formally defined as the expected value of the product of the deviations of each asset's return from its own expected return. This structure allows the matrix to capture the full second moment properties of the joint distribution of asset returns. The elements along the main diagonal of the covariance matrix, which are represented by sigma of I, I, represent the covariance of an asset's return with itself. This is by definition the variance of asset I denoted by sigma I square. Variance is the most common measure of a single asset's risk or volatility. It quantifies the dispersion or spread of an asset's returns and its average expected return. A larger variance signifies wider range of potential outcomes and therefore greater uncertainty and higher standalone risk. In the context of the full matrix, the diagonal elements provide a baseline measure of the risk inherent in each asset before considering its interactions with others in the portfolio. The true power of the covariance matrix in the portfolio theory comes from its off-diagonal elements, sigma ij, which represent the covariance between the returns of two distinct assets I and j. These terms quantify the interactive risk, the degree to which two assets' returns move in relation to one another. This co-movement is the critical ingredient of understanding the diversification. So, we can see technically three types of co-movements here. The first one is a positive covariance. A positive off-diagonal element indicates that the returns of asset I and asset j have a tendency to move in the same direction. When asset I experiences a return above its average, and asset j is also likely to be above its average and vice versa. Portfolios constructed with assets that are highly positively covariant offer limited diversification benefits, as a downturn in one is likely to be accompanied by a downturn in the other. Next, we have negative covariance where sigma of ij is less than 0. A negative element signifies an inverse relationship. The returns of two assets tend to move in the opposite directions. When asset I performs well, asset j tends to perform poorly. This property is the mathematical foundation of diversification. By combining assets with negative covariance, the poor performance of one asset can be buffered by the strong performance of another, leading to reduction in the overall volatility of the portfolio. The next is zero covariance. A zero covariance implies that there is no linear relationship between the returns of the two assets. Their movements are independent of one another, offering a moderate level of diversification. Now, let's look into the fundamental mathematical properties of covariance matrix. The covariance matrix is not just any square matrix. It possesses fundamental mathematical properties that are directly consequences of its statistical definition and its role in finance. The first one we'll look into is symmetry. The covariance matrix is always symmetric, meaning sigma of ij is equal to sigma of ji for all I and j. Or more compactly, sigma is equals to sigma transpose. The next property which we look into is positive semi-definiteness. A more profound and critical property is that any valid covariance matrix must be semi-positive definite. This is a more profound and critical property, and every covariance matrix must follow this property. Mathematically, this means that for any non-zero column vector of portfolio weights W, the quadratic form W transpose into sigma into W must be greater than or equal to 0. This is not merely a mathematical constraint, but a reflection of a fundamental financial reality. The total variance of a portfolio sigma p square is calculated precisely by this quadratic form. Sigma p square is equals to Wt sigma W. By its statistical definition, variance is the expected value of a squared deviation, which can never be negative. A portfolio with negative variance is physically and statistically impossible. Therefore, the requirements Wt sigma W should always be greater than or equal to zero for any convincible portfolio. Now let's look into how we can visualize risk using the covariance matrix. While the algebraic representation of covariance matrix is essential for computation, its geometric interpretation provides a far more intuitive understanding of portfolio risk and diversification. By visualizing the joint distribution of asset returns, the abstract numbers within the matrix transform into a tangible shape that reveals the structure of the risk. Now consider a simple portfolio of two assets. If we plot their historical returns on a two-dimensional scatter plot, we typically observe a cloud of points. The shape, spread, and orientation of this cloud contain all the information encoded in the 2 into 2 matrix, which is the covariance matrix. A common and mathematically convenient assumption in finance is that asset returns follow a multivariate normal distribution. Under this assumption, the scatter plot of returns can be elegantly summarized by a series of concentric ellipses known as isoprobability or isodensity contours. Each ellipse connects points of equal probability density, forming a topographical map of return distribution. The innermost ellipse represents the regions of higher probability where the returns are most likely to fall, while the outer ellipses represent the less likely and more extreme outcomes. The center of this family of ellipses is located at the vector of mean returns u is equals to u1, comma u2 of transpose. Crucially, the shape and size and orientation of every ellipse are determined entirely by the 2 into 2 covariance matrix. So, for the 2 into 2 covariance matrix, we can represent each element as this. Its principal diagonal elements are sigma 1 square and sigma 2 square, and the other elements are equal, which are rho 1 2 into sigma 1 sigma 2 and rho 1 2 into sigma 1 sigma 2. The diagonal elements sigma 1 and sigma 2 dictate the spread of the ellipse and the primary axis if there were no correlation. The off-diagonal elements, which depends on the correlation coefficient rho 1 2, determines the ellipse tilt and thickness, revealing the nature of the co-movement between two assets. The power of the risk ellipse lies in the ability to provide a clear visual metaphor for diversification, one of the central concepts of MPT. The orientation and eccentricity of the ellipse are directly tied to the correlation between the assets and consequently to the potential benefits of combining them in a portfolio. When the assets are positively correlated, their returns tend to move together. Geometrically, this is represented by an ellipse that is elongated and tilted at a positive 45-degree angle. When assets are negatively correlated, their returns tend to move in opposite directions. The resulting ellipse is elongated but tilted at a negative 45-degree angle. If the assets are not correlated or uncorrelated, the covariance term is zero, and the risk ellipse's major and minor axes will be aligned with the horizontal and vertical coordinate axis. This ellipse will only be a perfect circle if the individual variances sigma 1 square and sigma 2 square are equal. The geometric interpretation of the covariance matrix as a risk ellipse can be made mathematically precise through the powerful linear algebra technique of eigen decomposition. This process breaks down the complex correlated risk structure of a portfolio into a set of independent principal sources of risk, offering deep insights for risk management and portfolio construction. The eigenvectors of the covariance matrix are a set of orthogonal vectors that define the principal axis of the risk ellipse. They represent the fundamental directions of variance with the data. The first eigenvector, or the vector associated with the largest eigenvalue, often called the principal eigenvector, points along the major axis of the risk ellipse. This is the direction in which the data is most spread out and represents the single most dominant source of risk in the portfolio. In financial markets, this often corresponds to a market factor, a broad movement that affects all the assets to some degree. The second eigenvector is orthogonal to the first and points along the minor axis of the ellipse, representing the direction of the next largest source of variance that is independent of the first in a portfolio with n assets. In a portfolio with n assets, there will be n orthogonal eigenvectors, each identifying an independent source of risk ordered from most to least significant. Each eigenvector Vi has a corresponding scalar value called the eigenvalue, which is denoted by lambda of I. The eigenvalue quantifies the amount of variance in the data along the direction of its associated eigenvector. Geometrically, the square root of the eigenvalue or root over of lambda I is directly proportional to the length of the semi-axis of the risk ellipse and in the direction of Vi. The largest eigenvalue, lambda 1, therefore measures the variance along the principal axis of the risk, quantifying the magnitude of the portfolio's single greatest risk exposure. The proportion of the total portfolio variance that is explained by this primary risk factor can be calculated as the ratio of the largest eigenvalue to the sum of all eigenvalues. The formula can be written as this: lambda 1 by the sum of all eigenvalues from 1 to n. Now let's look into a few practical insights from eigendecomposition. The eigendecomposition of a covariance matrix is not just a mathematical exercise. It provides a powerful framework for understanding and managing portfolio risk. It forms the basis of principal component analysis, a technique widely used in quantitative finance to identify the main drivers of the portfolio returns and risks. The eigenvectors are more than just abstract directions. They can be interpreted as specific constructible portfolios. A portfolio whose asset weights are set to the components of a given eigenvector is an eigenportfolio. This portfolio has the unique property that its risk is entirely concentrated along the direction of the eigenvector. To see this, consider an eigenportfolio with weights W equal to a unit vector V. The variance of this portfolio is given by the standard formula. Sigma p square is equals to the transpose of the weights matrix into covariance matrix into the weights matrix, which can be then written as Vt into covariance matrix into V, where V is the eigenvector. Now, from the definition of eigenvectors, we know that covariance matrix multiplied by V, or the eigenvector, is equal to the same product as the eigenvalue of the eigenvector multiplied to the eigenvector. Substituting this into the variance equation yields variance is equals to eigenvector transpose into the multiplication of the scalar eigenvalue into the eigenvector. Now we can bring the scalar out, and the equation will become lambda into the product of V transpose into V. Now, since V is a unit vector, its dot product with itself, VTV, is equals to 1. Therefore, the variance of the eigenportfolio simply is its corresponding eigenvalue. This remarkable result reveals that eigenvectors represent the portfolios with pure exposure to a single independent source of risk. The portfolio constructed from the first eigenvector is maximally exposed to the dominant risk factor in the market, and its variance is precisely lambda 1. The portfolio built from the second eigenvector is exposed only to the second largest independent risk factor with variance lambda 2, and so on. The geometric and algebraic properties of covariance matrix culminate in their application to the Markowitz modern portfolio theory, specifically in the derivation of the efficient frontier. The shape of this famous curve, which represents the optimal trade-off between risk and return, is not arbitrary, but is a direct mathematical consequence of the portfolio's underlying covariance structure. The central equation in MPT for quantifying portfolio risk is the formula for portfolio variance, expressed in the matrix notation as the quadratic form. Portfolio variance is equals to the transpose of the weights matrix into the covariance matrix into the weights matrix. Here, W represents the column vector of the portfolio weights matrix, and WT is a transpose. This compact equation elegantly synthesizes all the risk information, the individual asset variances, the interactive co-movements, and the portfolio allocations into a single scalar value representing the total portfolio risk. The efficient frontier is the set of all optimal portfolios for a universe of only risky assets. It is found by solving a constrained optimization problem for each possible level of expected portfolio return UP. You find the portfolio weight vector W that minimizes the portfolio variance sigma p squared. This minimization is subject to two constraints. One is that the portfolio's expected return must be equal to the target sum or target return, and the total sum of the weights must be equal to 1. The solution to this quadratic problem, typically found using the method of Lagrange multipliers, establishes a direct mathematical relationship between the minimum achievable variance and the target return. This relationship is a parabola in the mean variance plane, and consequently a hyperbola in the mean standard deviation plane. This characteristic hyperbolic shape is often referred to as the Markowitz bullet. A rational risk-averse investor will only consider portfolios on the upper half of this hyperbola, as any portfolio on the lower half is inefficient, as another portfolio exists with the same level of risk but a higher expected return. This upper boundary is the efficient frontier. The precise shape and location of this frontier are dictated by the covariance matrix. The explicit formula for the parabolic relationship between the variance and mean is variance of the portfolio is equals to 1 by d multiplied by S11 into UP square minus 2S1 mu into UP plus SUU, where the scalar coefficients S11, S1U, and SUU and D are all functions of the inverse of the covariance matrix, and the vector of expected return U. The shape of a parabola is defined by its coefficients. They determine its curvature and the location of its vertex. Since these coefficients are calculated directly from the inverse of the covariance matrix, the covariance matrix acts as a geometric engine that generates the entire set of possible risk-return trade-offs. Any change in the underlying risk structure, for instance, a decrease in the correlation between two assets, will alter the elements of the covariance matrix, which in turn changes the entire inverse of the covariance matrix. This recalculates the coefficients of the parabola, thereby reshaping the efficient frontier. Generally, lower correlations among assets will cause the frontier to become more curved and shift to the left, indicating that the lower levels of risk are more achievable for any given level of return. This highlights the critical importance of accurately estimating the covariance matrix. A noisy or unstable estimate will lead to a distorted and unreliable efficient frontier, resulting in suboptimal portfolio construction. The covariance matrix is far more than a static table of numbers. It is a dynamic mathematical construct that provides the foundation for quantifying, visualizing, and managing portfolio risk. Its algebraic components, which are the variances on the diagonal and covariances on the off-diagonal elements, give a complete numerical description of individual and interactive asset risks. Transitioning from algebra to geometry, the covariance matrix manifests as a risk ellipse, a powerful visual tool that makes abstract concepts like correlation and diversification intuitive. Finally, these geometric and algebraic properties converge in the formulation of the Markowitz efficient frontier. The covariance matrix acts as the engine that generates the precise shape of the risk-return trade-off, defining the hyperbolic boundary of optimal portfolios for risky assets and determining the maximum achievable risk-adjusted return when a risk-free asset is available. The journey from a single matrix element to the grand architecture of efficient frontier demonstrate the profound and elegant connection between the abstract linear algebra and the practical science of modern portfolio management. Thank you.